In the cold silence of the solar system, there spins a world we have named, mapped, and claimed to understand. Mars, the red planet, our celestial neighbor. We have sent robots to crawl across its surface, satellites to orbit its skies, and dreams to colonize its future. We speak of Mars as if it were a solved mystery, a chapter already written in the book of planetary science. But what if everything we think we know about Mars is only the surface of a far deeper truth? What if the red planet is not what we have been led to believe, and the real Mars, the hidden Mars, has been waiting all along for us to ask better questions? Tonight, we will peel back the layers of assumption and peer into the scientific shadows where Mars reveals itself not as a dead, dusty world, but as a planet of profound mysteries that challenge the very foundation of planetary science. The Mars in textbooks, in documentaries, in the collective imagination, is a story half told, a narrative simplified for convenience, polished for popular consumption. But beneath that familiar tale lies another Mars entirely, one that scientists are only beginning to glimpse through instruments sensitive enough to detect what has always been there, hidden in plain sight. In popular culture, Mars is simple. It is the barren desert planet, the frozen wasteland, the place where water once flowed in ancient rivers, but now exists only as ice locked beneath polar caps. It is the world where life, if it ever existed at all, died billions of years ago, leaving nothing behind but a geological graveyard. This is the Mars of movies and headlines, the Mars that fits neatly into our expectations, a cautionary tale about climate change, a stepping stone for human exploration, a planet that once resembled Earth but lost its way. Yet this comfortable narrative, repeated so often it has become truth, is beginning to crack under the weight of new discoveries. Instruments designed with unprecedented sensitivity are detecting atmospheric signatures that should not exist. Orbital mapping reveals geological features that defy conventional timelines. Subsurface radar paints pictures of complexity where simplicity was expected. And slowly, methodically, the scientific community is being forced to admit that Mars is not behaving the way a dead planet should. The question is not whether Mars holds secrets. The question is, how much of what we thought we knew must now be unlearned? Consider this. We have been looking at Mars through the lens of Earth, assuming that planetary evolution follows a single predictable path. We have projected our own geological story onto a world that may have written its history in an entirely different language. What if the water on Mars did not simply vanish into space? What if the atmosphere we believe was stripped away is still there, hiding beneath the surface in forms we are only now learning to detect? What if the line between ancient Mars and modern Mars is not as clear as we have drawn it? These are not fringe theories whispered in dimly lit conferences. These are questions emerging from data returned by our most sophisticated missions. Questions that do not have easy answers, because they require us to reimagine what a planet can be. Before we venture deeper into this hidden science, before we explore the anomalies that do not fit, the discoveries that rewrite timelines, and the biological possibilities that refuse to be dismissed, I would like to invite you into this journey more personally. Wherever you are in the world right now, whatever time it is as you listen to these words, you are part of a global community of curious minds drawn to the edges of understanding. Please take a moment to leave a comment. Tell us where you are watching from, and what time it is in your corner of the world. Are you drifting towards sleep under the stars of the southern hemisphere, waking to dawn in Asia, finding a quiet moment in the afternoon? This question connects us all, viewers scattered across Earth, united by curiosity about a world millions of miles away. Now, settle deeper into this moment. Let your thoughts expand beyond the familiar. Because the Mars we are about to explore is not the Mars of childhood wonder or science fiction simplicity. It is a Mars that scientists are still learning to see, a planet that holds its secrets close and reveals them only to those willing to look beyond the surface. The hidden science that changes everything is not hidden because it is secret. It is hidden because we have not yet learned to ask the right questions. Our journey begins not with answers, but with doubt, the most fertile ground for discovery. Let us start by questioning everything we think we know. Mars presents us with a cosmic riddle wrapped in rust-colored dust. It is a world that simultaneously whispers of life and screams of death, a planet caught between two incompatible stories. On one hand, we see the unmistakable signatures of ancient rivers, vast oceans, and a climate that could have cradled life billions of years ago. On the other, we face a barren wasteland bombarded by deadly radiation, stripped of atmosphere, and frozen into perpetual hostility. How can both of these narratives be true? How did a world that once resembled Earth transform into a monument to desolation? The paradox begins with water. Rovers crawling across the Martian surface have discovered riverbeds carved deep into ancient stone, deltas that once fanned outward from flowing channels, and minerals that form only in the presence of liquid water. These are not subtle hints, they are emphatic declarations that Mars was once a world where water pooled, flowed, and perhaps even rained from clouded skies. Yet today, liquid water cannot exist on the Martian surface. The atmospheric pressure is too low, the temperature too cold. Any droplet exposed to the thin air would either freeze instantly or evaporate into vapor within seconds. This is not merely a change in weather patterns. This is planetary transformation on a scale almost incomprehensible. The Mars that carved those valleys is not the Mars we see today. Something catastrophic happened. Something that fundamentally altered the planet's ability to sustain the very element that defines habitability. The answer lies partially in what Mars lost, its magnetic field. Earth is protected by an invisible shield generated deep within its core, where molten iron churns in continuous motion, creating a magnetic cocoon that deflects the solar wind, the relentless stream of charged particles flowing from the sun. Mars once had such a field. Evidence from magnetized rocks in the Martian crust tells us that billions of years ago, Mars too possessed this protective barrier. But then, mysteriously, it vanished. Without a magnetic field, Mars became vulnerable. The solar wind, no longer deflected, began to strip away the atmosphere molecule by molecule, ion by ion, year after year, for billions of years. What was once a thick blanket capable of trapping heat and maintaining liquid water gradually thinned into the wispy veil we observe today. The radiation that Earth's magnetic field repels now bathes the Martian surface directly, bombarding the soil with particles energetic enough to sterilize any organic molecules that might exist there. Why did Mars's magnetic field fail? The leading hypothesis centers on the planet's core. Earth's core remains hot and active, sustained by radioactive decay and residual heat from our planet's formation. Mars, being smaller, cooled faster. Its internal dynamo sputtered and died, perhaps as early as 4 billion years ago. Without the churning motion of liquid metal, the magnetic field collapsed. The planet's fate was sealed not by external catastrophe, but by internal silence, by the gradual cooling of its heart. Yet even this explanation raises more questions. Why did Earth's core remain active while Mars's did not? Size alone cannot account for every difference. Venus, similar in size to Earth, also lacks a substantial magnetic field, yet retained a thick atmosphere through different mechanisms. The solar system, it seems, does not follow simple rules. Each world's story is shaped by subtle variations in composition, formation history, and cosmic timing. Mars harbours another paradox in its very structure. The planet is divided, almost literally split, into two distinct faces. The northern hemisphere consists largely of smooth, low-lying plains, some of the flattest surfaces in the solar system. The southern hemisphere is ancient, cratered, and elevated, rising several kilometers higher on average than the north. This dramatic divide, known as the Martian dichotomy, represents one of the most striking features in planetary science. Several theories attempt to explain this split personality. One suggests a colossal impact early in Mars's history, a collision so violent it excavated the entire northern basin, creating a hemispherical scar that never fully healed. Another proposes internal processes, massive convection currents within the young planet's mantle that created asymmetric features. Some researchers even wonder if Mars once had plate tectonics that operated differently than Earth's, concentrating volcanic activity in one hemisphere while leaving the other untouched. What makes the dichotomy particularly intriguing is what it suggests about Mars's geological timeline. If the northern plains were indeed created by impact, that event must have occurred very early, when Mars was still geologically active enough to partially resurface the wounded region. If it arose from internal processes, it implies a planetary engine more complex than Mars's small size would suggest. Either way, the dichotomy tells us that Mars's evolution was neither simple nor predictable. The geological record itself refuses to fit neatly into our models. Dating Martian surface features reveals puzzling inconsistencies. Some regions show evidence of volcanic activity far more recent than the planet's presumed geological death. Certain lava flows appear to be only a few million years old, perhaps even younger, raising the possibility that Mars is not entirely dormant, but merely sleeping. Water-carved features also span an enormous range of ages, suggesting that Mars experienced multiple wet periods separated by long dry intervals, rather than a single transition from wet to dry. These findings challenge the comfortable narrative of Mars as a planet with a straightforward history. Instead, they present a world of intermittent activity, of cycles we do not yet understand, of a planet that repeatedly surprised itself with brief returns to warmth and wetness, even as it marched inexorably toward its current frozen state. Perhaps nothing embodies Mars's mysteries more than the methane detections. Methane is a simple molecule, 4 hydrogen atoms bound to 1 carbon atom, but on Mars it should not persist. Ultraviolet radiation from the sun breaks down methane within a few hundred years. Any methane detected in the Martian atmosphere must therefore be recently released, either from geological processes deep underground or, tantalizingly, from biological activity. Observations from orbit and from rovers on the surface have detected methane plumes appearing and disappearing with confounding irregularity. Some measurements show spikes in methane concentration that rise and fall with the Martian seasons. Others find methane in certain locations, but not others. The gas appears, vanishes, and reappears without clear pattern or explanation. Scientists have proposed numerous sources. Methane could be released from underground reserves trapped in ice-like structures called clathrates, liberated when seasonal temperature changes crack the frozen soil. It could emerge from water-rock reactions occurring in subsurface aquifers, a process that requires liquid water but no life. Or in the scenario that captures imaginations most powerfully, it could be produced by microorganisms living beneath the surface, metabolizing and exhaling methane as a waste product, invisible to us but chemically announcing their presence. We do not yet know which explanation is correct. Perhaps all of them contribute. Perhaps none fully account for what we observe. The methane mystery reminds us that Mars still holds agency in its own story, still possesses the capacity to surprise us, to reveal that our understanding remains incomplete. Mars defies logic not because it is inconsistent, but because it operates on scales and through processes that challenge our Earth-based intuitions. It is a planet that was once habitable and is now hostile, a world that lost its atmosphere yet still whispers of hidden water, a sphere divided against itself geologically, a body that should be dead yet continues to release gases into its thin air. To study Mars is to confront paradox directly, to accept that the universe is under no obligation to make sense on our terms. The contradictions we observe are not errors in our measurements. They are invitations to think more deeply, to question our assumptions, to recognize that planetary evolution is not a simple linear progression, but a complex dance of forces, timing, and chance. As we peer at Mars through telescopes and rovers, examining each rock and analyzing each wisp of atmosphere, we are not simply gathering data, we are learning humility. Mars teaches us that even a small, cold, seemingly simple world can contain mysteries that span billions of years, paradoxes that reshape our understanding of how planets live, change, and perhaps against all odds, sustain the spark of life in the darkness. Before Mars became the silent, rust-coloured world we observe through our telescopes today, it was something else entirely, something almost unrecognisable. 3 to 4 billion years ago, during a period scientists call the Noachian epoch, Mars may have been a world of blue skies and flowing water, a planet where clouds drifted across horizons and rain fell upon ancient shores. This is not speculation born from wishful thinking. It is a portrait painted by evidence, written in stone across the Martian surface, waiting patiently for billions of years to be read. To imagine ancient Mars is to picture a world transformed, where today we see endless dusty plains and lifeless valleys. There may once have been lakes that stretched to distant horizons. Where rusted iron oxides now coat every surface, there might have been riverbanks lined with sediment, deltas where water met standing bodies in intricate patterns of deposition. The Mars that was is not the Mars we know, and understanding this vanished world changes everything about how we view our neighbouring planet. The evidence for ancient water on Mars is not subtle. It is carved into the planet's face with undeniable clarity. From orbit, spacecraft have mapped vast, networks of valley systems that branch and merge exactly as rivers do on Earth. These are not random cracks in the surface. They are drainage systems, channels that carried flowing water downhill, following gravity's patient pull over thousands or millions of years. Some of these valleys stretch for hundreds of miles, winding through ancient highlands like the ghosts of rivers that ran dry before multicellular life arose on Earth. Perhaps most compelling are the deltas. In regions like Jezero Crater, where NASA's Perseverance rover now explores, orbital images reveal fan-shaped deposits of sediment that mirror the deltas formed wherever rivers meet lakes or seas on our own world. These formations require not just water, but persistent water, flowing steadily enough to transport rock and soil and deposit them in layered patterns that can only form over extended periods. A brief flood might carve a channel, but a delta speaks of seasons, of cycles, of time measured not in days, but in geological ages. Clay minerals tell an even deeper story. Rovers and orbiters have detected phyllosilicates, clays that can only form in the presence of liquid water over long timescales. Unlike minerals created by brief interactions with moisture, these clays require water to remain in contact with rock for years, centuries, perhaps millennia. They are chemical signatures of stability, evidence that ancient Mars did not merely experience occasional floods, but sustained environments where water pooled, percolated through soil, and slowly transformed the mineralogy of the planet's crust. But water alone is not enough to explain ancient Mars. Liquid water cannot exist on a planet's surface without sufficient atmospheric pressure and warmth. Today, Mars's atmosphere is less than 1% as thick as Earth's. Water exposed to this thin air would either freeze instantly or evaporate into the void. For ancient Mars to host rivers and lakes, it must have possessed something it has long since lost. A thick, protective atmosphere capable of maintaining temperatures above freezing and pressure sufficient to keep water in its liquid state. What could have sustained such an atmosphere? This question lies at the heart of Martian science. Some researchers propose that volcanic activity, far more intense in Mars's youth, continuously released gases into the atmosphere, creating a greenhouse effect that trapped heat and warmed the planet's surface. Carbon dioxide, water vapor, and perhaps methane would have formed an insulating blanket, allowing sunlight to warm the ground while preventing heat from escaping back into space. Under these conditions, Mars might have experienced a climate not entirely unlike Earth's, though likely colder, with average temperatures hovering just above the freezing point of water. Others suggest that Mars's early atmosphere may have been thickened by impacts. During the late heavy bombardment, approximately 4 billion years ago, the inner solar system was pelted by asteroids and comets. These collisions would have delivered not just destruction, but also volatiles, water ice, and gases trapped within the impactors. Each major impact could have temporarily enriched Mars's atmosphere, creating windows of habitability that lasted thousands or even millions of years before slowly fading as gases escaped into space. The possibility of ancient Martian rainfall captures the imagination in ways that statistics about atmospheric pressure cannot. Picture clouds gathering over ancient highlands, darkening skies that had perhaps never been photographed by human eyes, but existed nonetheless. Imagine droplets forming in the cold Martian air, falling through an atmosphere thick enough to carry them gently to the ground, rather than evaporating mid-descent. rain pooling in low-lying areas, filling craters that became lakes, feeding rivers that carved their patient paths toward lowland basins where seas may have collected, dark and cold, under a salmon-colored sky. Some scientists have even modeled ancient Martian weather systems, attempting to reconstruct wind patterns, precipitation cycles, and seasonal variations. If Mars possessed oceans, it would have had evaporation. If it had evaporation, it would have had clouds. And if it had clouds, it would have experienced weather, the daily drama of temperature shifts, storms, perhaps even snow on high peaks and fog in sheltered valleys. These are not fantasies. They are logical consequences of the physical evidence we observe today. The most tantalizing question is not whether ancient Mars had habitable conditions, but for how long they persisted. Was wet Mars a brief phase, lasting only a few 100 million years before conditions deteriorated? Or did liquid water persist for 1 billion years or more, providing a stable environment where, hypothetically, life might not only emerge, but evolve, adapt, and perhaps even thrive in forms we cannot yet imagine? Geological evidence suggests the answer may lie somewhere in between. The Noachian period, when most of the valley networks formed, lasted roughly 400 million years. That is a vast expanse of time, longer than the entire Phanerozoic eon on Earth, the period during which complex life evolved from simple organisms into the diversity we see today. If Mars remained habitable for even a fraction of that time, the implications are profound. Yet the evidence also shows that Mars's transformation was not instantaneous. The transition from wet to dry did not happen overnight. Instead, Mars appears to have experienced a gradual decline, periods of habitability interrupted by harsher conditions, episodic flooding followed by long dry spells. Some regions may have retained liquid water far longer than others, creating refuges where Martian environments persisted even as the planet as a whole grew colder and drier. What caused this dramatic transformation remains one of planetary science's most compelling mysteries. Mars is smaller than Earth, with only about 1/10 our planet's mass. This fundamental difference had cascading consequences. A smaller planet cools faster. As Mars's interior cooled, volcanic activity declined, reducing the supply of atmospheric gases. Without continuous replenishment, gases slowly escaped into space, stripped away by solar wind that battered the planet's thinning atmosphere. Mars also lacks a global magnetic field, a protective shield that on Earth deflects charged particles from the Sun. Ancient Mars may have had such a field early in its history, generated by a molten core churning with convective currents. But as the core cooled and solidified, the magnetic field faded, leaving the atmosphere vulnerable. Over millions of years, solar wind eroded the upper atmosphere, molecule by molecule, until the thick blanket that once warmed the planet had become the gossamer veil we observe today. To stand on ancient Mars, had such a thing been possible, would have been to witness a world in transition, a planet that had once been vibrant, slowly dimming, rivers slowing to trickles, lakes evaporating into basins of salt, skies thinning until stars became visible even at midday. The transformation was geological, measured in epochs beyond human comprehension, yet it was also absolute. By the time Mars entered the Amazonian period, the current epoch that has lasted more than 3 billion years, the planet had become the cold, dry desert we recognize today. But the story of ancient Mars is not a tale of loss alone. It is also a record preserved with extraordinary fidelity. Unlike Earth, where plate tectonics constantly recycle the surface and erosion wears away ancient landscapes, Mars is geologically quiet. Its surface is a museum, a frozen archive where the distant past remains visible, etched into plains and mountains, waiting for explorers to decipher the history written there. Every valley we trace from orbit, every delta we examine with rovers, every clay deposit we analyze with spectrometers adds another line to this ancient narrative. We are reading a planetary biography, reconstructing the life story of a world that evolved along a different path than our own. Ancient Mars shows us that habitability is not permanent, that planets can change fundamentally, and that the conditions necessary for life, if they exist at all, may be fleeting on cosmic timescales. As we piece together this vanished world, we are reminded that Mars was not always the silent neighbor we observe today. It was once dynamic, perhaps even beautiful in its own alien way. And somewhere beneath the dust, locked in ancient rocks and buried ice, the memory of that world remains, waiting to reveal whether Mars, in its blue period, ever knew life. We stand now at the edge of a profound mystery, one written not in what Mars is, but in what Mars has lost. The red planet before us is incomplete, a world missing vital pieces of itself. Somewhere in the passage of time, Mars shed its atmosphere, its magnetic shield, perhaps even oceans that once lapped against ancient shores. To understand Mars is to become detectives of planetary loss, tracing the invisible pathways through which a world can dissolve into space itself. The atmosphere we observe today is thin beyond comprehension. At the surface of Mars, the air pressure is less than 1% of Earth's, barely enough to sustain even the faintest breeze. Yet the evidence scattered across the Martian landscape tells a different story. River valleys carved deep into stone, deltas where ancient waterways once met standing lakes, minerals that form only in the presence of liquid water. All of these features whisper the same truth. Mars once held an atmosphere thick enough, warm enough, to support flowing water on its surface. The question that haunts planetary scientists is both simple and profound. Where did it go? The leading theory points upward, toward the Sun. Without a protective magnetic field, Mars stands naked before the solar wind, a relentless stream of charged particles that flows outward from our star at speeds exceeding 1,000,000 miles per hour. On Earth, our magnetic field acts as an invisible shield, deflecting these particles around our planet and preserving our atmosphere. But Mars lost its magnetic dynamo billions of years ago, and with it, any defense against the solar wind's erosive power. Year by year, century by century, millennium by millennium, the solar wind strips away the upper layers of Mars's atmosphere, molecule by molecule, sending them tumbling into the void of space. NASA's MAVEN spacecraft, which has orbited Mars since 2014, has measured this atmospheric escape in real time. The data is sobering. Mars currently loses hundreds of tons of atmosphere to space every single day. During solar storms, when the sun's activity intensifies, this loss accelerates dramatically. The solar wind does not merely blow past Mars, it tears at the planet, stripping away the very air that once made it a warmer, wetter world. Over billions of years, this patient theft has transformed Mars from a planet that might have resembled Earth into the cold desert we observe today. But atmospheric escape is only part of the story. Another theory suggests that catastrophic impacts may have played a role. When massive asteroids collided with Mars in its ancient past, The kinetic energy released would have been staggering, enough to superheat portions of the atmosphere and blast enormous volumes of gas directly into space. These impacts would have acted like planetary explosions, each one ejecting not just rock and debris, but precious atmosphere that Mars could never reclaim. Some scientists propose that the largest impacts could have stripped away significant fractions of the atmosphere in single violent events, reshaping Mars in moments that lasted only hours, but echoed across eons. The loss of Mars's magnetic field remains one of planetary science's most compelling puzzles. Earth's magnetic field is generated by convection currents in its liquid iron core, a geodynamo that has operated for billions of years. Mars once possessed a similar dynamo. We know this because ancient Martian rocks, particularly in the southern highlands, retain magnetic signatures locked into their structure when they solidified. These rocks remember a time when Mars had a global magnetic field, perhaps as strong as Earth's. Then, somewhere between 3 and 4 billion years ago, that field vanished. Why did Mars's dynamo fail? Several competing explanations exist, each supported by fragments of evidence. One theory suggests that Mars simply cooled too quickly. Being smaller than Earth, Mars has a larger surface area relative to its volume, allowing heat to escape more efficiently. As the core cooled, convection currents weakened and eventually ceased, shutting down the magnetic field. Another hypothesis points to a massive impact that disrupted the core's flow patterns, perhaps the same collision that created the enormous Hellas Basin, a crater so vast it could swallow the Mediterranean Sea with room to spare. A third possibility involves the planet's interior composition, suggesting that Mars's core may have crystallized or differentiated in ways that made sustaining a dynamo impossible. The truth may involve all of these factors, or none of them. What remains certain is that the loss of Mars's magnetic field was catastrophic for its atmosphere. Once the shield fell, the solar wind had unrestricted access to Mars's upper atmosphere, beginning the long process of atmospheric erosion that continues to this day. Then there is the missing mass problem, the vast quantities of water that once existed on Mars but have seemingly vanished. When scientists study the Martian landscape, they see undeniable evidence of abundant water. Valleys that could only have been carved by rivers, shorelines that mark ancient ocean boundaries, hydrated minerals spread across vast regions. By some estimates, early Mars may have held enough water to cover the entire planet in an ocean hundreds of feet deep. If we gathered all the water vapor and ice currently visible on Mars, we would find only a tiny fraction of this ancient abundance. Where did it go? The answer lies partly in isotope ratios, the subtle differences in atomic weights that serve as fingerprints of planetary history. Water molecules contain hydrogen atoms, and hydrogen comes in two main varieties: ordinary hydrogen and its heavier cousin, deuterium. When Mars lost its atmosphere, lighter hydrogen atoms escaped to space more easily than heavier deuterium atoms. Over time, this selective loss enriched Mars's remaining water in deuterium. When we measure the deuterium to hydrogen ratio in Martian water vapor today, we find it is 5 to 7 times higher than in Earth's oceans. This enrichment tells us a story of massive loss, of an atmosphere that once held far more water than we see now, water that gradually leaked away into space across billions of years. But not all of Mars's water escaped. Some remains hidden, locked away in reservoirs we are only beginning to discover. The polar ice caps contain vast quantities of frozen water mixed with carbon dioxide ice, seasonal layers that record climate cycles stretching back millions of years. Beneath the surface, ground-penetrating radar has detected what appear to be massive deposits of underground ice extending from the poles toward the equator, buried beneath protective layers of dust and rock. Some estimates suggest that if we could melt all the ice currently trapped beneath Mars's surface, we might recover enough water to form a global ocean several meters deep. In 2018, radar data from the European Space Agency's Mars Express orbiter revealed something even more intriguing. What appears to be a lake of liquid water buried beneath the southern polar ice cap, kept liquid by salt dissolved in the water and the pressure of overlying ice. If confirmed, this would be the first stable body of liquid water found on Mars, a hidden reservoir that has persisted despite the planet's frigid, arid surface conditions. Other potential underground lakes may await discovery, pockets of liquid brine sheltered from the harsh surface environment, perhaps even preserved since Mars's ancient past. The story of Mars's lost elements is not one of sudden catastrophe alone, but of gradual erosion punctuated by devastating events. Both processes worked in tandem, reshaping a world that once might have harbored life into the stark landscape we observe today. Yet even in loss, there is preservation. The water locked in polar ice, the atmosphere still clinging to the surface, the magnetic anomalies frozen in ancient rock. All of these are pieces of the puzzle, clues that allow us to reconstruct what Mars once was. As we contemplate these missing elements, we realize that Mars is not simply a dead world. It is a world in transformation, still changing, still evolving, albeit far more slowly than in its turbulent youth. The solar wind continues its patient work. The seasons still cycle ice from pole to pole, and deep beneath the surface, hidden reservoirs wait in darkness. Mars has not ended its story. It has merely moved from one chapter to another, from a world of flowing water and thick atmosphere to a world of ice and memory. Every missing piece tells us something essential about planetary evolution, about the delicate balance required to sustain an atmosphere, about the role of magnetic fields in preserving habitability. Mars is not just Mars. It is a cautionary tale, a reminder that worlds can change, that the conditions we take for granted on Earth are not permanent features of planetary existence, but temporary states that must be actively maintained by geological and magnetic processes. In seeking Mars's lost elements, we are seeking to understand not only where they went, but what they mean for the future of planetary exploration. If we are to one day make Mars habitable again, we must first understand how it became uninhabitable. The missing puzzle pieces are not merely historical curiosities. They are roadmaps showing us the challenges ahead and the forces we must consider if humanity is ever to walk freely beneath Martian skies, breathing air that was lost billions of years ago, but perhaps could one day be reclaimed. What if the Mars we photograph from orbit, with its rust-colored deserts and towering volcanoes, is merely a surface waiting to be peeled back? What if the true story of Mars exists not in the thin air above, but in the hidden darkness beneath? As we journey deeper into understanding this world, we arrive at a profound realization. The secrets of Mars may not be written across its surface at all. They may be buried, locked away in ice, stone, and perhaps even liquid water, waiting in chambers we have only begun to glimpse. Mars is not just a planet of dust and rocks. It is a world with layers, with depth, with hidden architecture carved over billions of years. Beneath the surface that rovers photograph and satellites map, there exists another Mars entirely. A Mars of ice and shadow, of ancient lava tubes and underground reservoirs, of geological mysteries that challenge everything we thought we understood about planetary evolution. To comprehend Mars, we must learn to see not just with cameras pointed downward, but with instruments that peer through rock itself, listening for echoes of what lies hidden below. The journey into Mars's subsurface begins with water. Not the fleeting traces found in atmospheric vapor or the seasonal frost that decorates polar regions, but vast deposits of ice locked beneath the ground. Radar observations from orbiting spacecraft have revealed stunning evidence. Mars harbors enormous quantities of subsurface ice, extending far beyond the polar caps into mid-latitudes and possibly even equatorial regions. Some of these ice deposits are hundreds of feet thick, preserved beneath layers of dust and regolith that shield them from sublimation into the thin Martian atmosphere. In 2018, scientists announced a discovery that sent ripples through the planetary science community. Beneath Mars's south polar ice cap, roughly a mile below the surface, radar data suggested the presence of a liquid water lake spanning approximately 12 miles across. The temperatures there should be far too cold for liquid water to exist, hovering around -90 degrees Fahrenheit. Yet the radar signature was unmistakable, matching the profile of liquid rather than solid ice. How could this be possible? The answer may lie in salts, particularly perchlorates, dissolved in the water. These compounds act as antifreeze, dramatically lowering water's freezing point and allowing it to remain liquid in conditions that would normally solidify it instantly. This discovery was not without controversy. Some researchers questioned whether the radar reflections might come from clays or other minerals rather than water. Others pointed out that even with salts, maintaining liquid water at such depths and temperatures would require additional heat sources we haven't yet identified. Yet the possibility remains tantalizingly real. If liquid water exists beneath the Martian surface, it represents not just a geological curiosity, but a potential refuge, a place where chemistry continues, where reactions occur, where the boundary between geology and biology becomes blurred and uncertain. The subsurface ice deposits tell us something profound about Mars's history. They are not remnants of ancient oceans that evaporated long ago. They are reservoirs, preserved libraries of water that may have cycled through Mars's climate system over countless epochs. During periods when Mars's axial tilt changed dramatically, ice could have migrated from poles to equator and back again, redistributing water across the planet in patterns we are only beginning to understand. Some of this ice may be billions of years old, older than complex life on Earth, holding within its crystalline structure clues to Mars's atmospheric composition across deep time. But water ice is not the only hidden feature beneath Mars's surface. The planet is riddled with vast underground structures, chambers carved not by water but by fire. Ancient lava tubes, formed when rivers of molten rock flowed across the surface billions of years ago, created hollow tunnels as the outer layers cooled and hardened while molten lava continued flowing beneath. When the eruption ceased, these tubes remained, some large enough to swallow entire cities. Observations suggest that some Martian lava tubes could be hundreds of feet wide and miles long, dwarfing their counterparts on Earth and the Moon. These tubes are not merely geological curiosities. They represent sheltered environments, protected from the harsh radiation that bombards Mars's surface. Without a substantial magnetic field or thick atmosphere, Mars is exposed to cosmic rays and solar radiation that would be lethal to most known forms of life. Yet inside a lava tube, shielded by meters or even hundreds of meters of rock, conditions would be dramatically different. Temperatures would be more stable, radiation levels would drop to manageable levels, and if any subsurface ice exists nearby, seasonal temperature fluctuations might even allow for periodic melting, creating temporary liquid water environments. Some researchers have identified what appear to be collapsed sections of these tubes, visible from orbit as chains of circular pits descending into darkness. Imaging these openings is tantalizing. They are doorways into Mars's hidden architecture, invitations to explore spaces that have remained unchanged for billions of years. What exists inside? Are the walls coated with ancient mineral deposits? Do ice formations cling to the ceiling? Could microbial life, if it ever arose on Mars, have retreated into these protected chambers as the surface became increasingly hostile? The possibility of current geothermal activity adds another layer to this underground mystery. Mars is generally considered geologically dormant, its core having cooled over billions of years. Yet evidence suggests the story may be more complex. Recent detections of methane plumes in Mars's atmosphere, appearing and disappearing seasonally, have sparked debate. Methane can be produced by geological processes or by biological activity. On Earth, most atmospheric methane comes from living organisms, but volcanic activity and reactions between water and certain minerals can also generate it. On Mars, if methane is being released from underground sources, it suggests that something is happening beneath the surface, something active and ongoing. Some scientists propose that localized pockets of geothermal heat might still exist, perhaps in regions where radioactive decay in the crust generates warmth, or where deep fractures allow heat from the planet's interior to rise toward the surface. These warm zones, if they exist, could create environments where liquid water persists year-round, forming underground aquifers or hydrothermal systems. Such systems on Earth teem with life, organisms that thrive in darkness, feeding not on sunlight, but on chemical energy extracted from minerals and dissolved gases. The parallel is impossible to ignore. This leads us to one of the most profound concepts in modern planetary science: the possibility of a subsurface biosphere on Mars. Not life clinging desperately to the surface, exposed to radiation and desiccation, but life thriving in the depths, insulated from the hostile conditions above. If Mars ever harbored life, and if that life arose billions of years ago when the surface was warmer and wetter, the gradual deterioration of surface conditions would have created intense evolutionary pressure to move downward, to seek refuge beneath the ground where water and stability could still be found. This concept is not science fiction. It is scientifically plausible, based on what we know about life on Earth. Deep underground, miles below the surface, scientists have discovered thriving microbial ecosystems that have been isolated from the surface for millions of years. These organisms survive on chemical energy, extracting sustenance from reactions between water and minerals. They reproduce slowly, live for enormous spans of time, and exist in conditions that seem impossibly extreme. If life arose independently on Mars, or if it shares a common origin with Earth through material exchanged via meteorite impacts, then a subsurface biosphere is not just possible, It is, in some sense, expected. Yet despite decades of exploration, Mars's interior remains profoundly mysterious. We have landed rovers on the surface, orbited the planet with sophisticated instruments, and even placed a seismometer on the ground to listen for Marsquakes. That instrument, part of NASA's InSight mission, detected hundreds of seismic events, revealing that Mars is not geologically dead. The planet trembles, it shifts. Its interior structure, while cooler than Earth's, still holds secrets about how planets evolve, cool, and change over billions of years. InSight's data suggested that Mars's crust is thinner than previously thought, and that its core is larger and possibly still partially molten. This challenges earlier assumptions that Mars had fully solidified. A partially liquid core could mean that Mars once had a stronger magnetic field, one that protected its atmosphere and surface water from being stripped away by solar wind. Understanding why that magnetic field collapsed is crucial to understanding why Mars transformed from a potentially habitable world into the cold desert we observe today. The subsurface of Mars is not just geology, it is a frontier, a hidden dimension of planetary exploration where the most important discoveries may still await. To truly know Mars, we must learn to explore not just its surface, but its depths. Future missions may carry ground-penetrating radar to map subsurface ice with precision. Robotic explorers might descend into lava tubes, their lights piercing darkness that has existed since the solar system was young. Drills might penetrate through ice to reach liquid water, sampling environments that have been isolated for eons. As we contemplate what lies beneath Mars, we are reminded that exploration is not just about seeing what is visible, but imagining what remains hidden. The surface of Mars is a story written in dust and stone. The subsurface is a novel waiting to be opened, its pages bound in ice and rock, its chapters describing a world that may be far more dynamic, far more alive, than the barren landscape visible from above. In the darkness below, Mars may yet surprise us, revealing not just its past, but perhaps even its present, unfolding in chambers where light has never reached, and where time moves to a rhythm we have yet to comprehend. Beneath the rust-colored surface of Mars lies one of the most profound questions ever posed by humanity. Are we alone? The search for life on Mars is not merely scientific curiosity. It is a mirror held up to existence itself, asking whether the spark of biology can ignite beyond one world. Yet the answer, if it exists at all, is buried in layers of ambiguity, chemical signatures, and data that refuses to speak clearly. The biological question on Mars is not about finding little green inhabitants. It is about detecting the faintest whisper of metabolism, the ghostly remnants of ancient organisms, or perhaps the slow, persistent chemistry of microbial life still clinging to existence in hidden corners beneath the frozen soil. The story begins in 1976, when two robotic emissaries touched down on Mars, carrying with them humanity's first direct attempt to answer the question. NASA's Viking 1 and Viking 2 landers arrived on the Martian surface equipped with sophisticated biology experiments designed to detect signs of life. Each lander scooped up soil samples and subjected them to tests that would measure metabolic activity, the presence of organic molecules, and chemical reactions consistent with living organisms. The results were extraordinary, confusing, and maddeningly inconclusive. One experiment, the labeled release test, showed positive results. When nutrients were added to Martian soil, gases were released, suggesting something was consuming the nutrients and producing waste, exactly as living organisms would. Scientists watched with anticipation. Could this be it? The first evidence of extraterrestrial life? But another experiment, designed to detect organic molecules, the building blocks of life as we know it, returned negative results. No organics were found. The paradox was profound. How could there be metabolic activity without organic chemistry? The scientific community debated fiercely. Some believed the labelled release results indicated life. Others argued that unusual Martian chemistry, possibly involving oxidizing compounds like perchlorates in the soil, could explain the gas release without invoking biology. Nearly 5 decades later, the Viking results remain unresolved, a biological Rorschach test that scientists interpret differently depending on their perspective. The ambiguity teaches us something essential. Life, if it exists elsewhere, may not announce itself clearly. It may whisper in data we do not yet know how to interpret. Decades passed before humanity returned to Mars with the tools to search more deeply. In 2012, the Curiosity rover landed in Gale Crater, a vast basin that once held water billions of years ago. Curiosity carried instruments capable of analysing the chemical composition of Martian rocks and soil with unprecedented precision. What it discovered changed the conversation entirely. Organic molecules, carbon-based compounds that form the foundation of all known life, were detected in ancient mudstones. These molecules, including theophanes and benzene rings, were preserved in rocks over 3 billion years old. Their presence does not prove life existed, but it confirms that the ingredients for life were present on ancient Mars. Organic chemistry is not biology, but it is a prerequisite. Where there are organic molecules and liquid water, the possibility of life becomes not just speculation, but plausible science. Curiosity's discoveries prompted scientists to look inward, to Earth's most extreme environments, searching for clues about what life on Mars might resemble. Enter the extremophiles, organisms that thrive in conditions once thought incompatible with life. In the boiling acidic springs of Yellowstone, in the frozen lakes beneath Antarctica's ice, in deep ocean vents where sunlight never reaches, and, in the radioactive depths of abandoned mines, life persists. Bacteria survive in temperatures exceeding 250 degrees Fahrenheit. Others endure total darkness, feeding on chemicals rather than sunlight. Some microbes withstand radiation levels thousands of times higher than what would kill a human. Tardigrades, microscopic animals known as water bears, can survive the vacuum of space, extreme dehydration, and temperatures near absolute zero. These extremophiles are not anomalies. They are evidence that life is not fragile. It is adaptable, resilient, and opportunistic. If life can exist in Earth's harshest environments, then perhaps it can exist, or could have existed, in the subsurface brines of Mars, shielded from radiation, sustained by geochemical energy rather than sunlight. Yet another mystery deepens the biological question: the methane enigma. Methane has been detected in Mars's thin atmosphere multiple times, appearing seasonally and in localized plumes. On Earth, methane is produced primarily by biological processes, the waste product of microbes digesting organic material. But methane can also form through geological processes, such as the reaction of water with certain minerals in the presence of heat. The question is not whether methane exists on Mars, but where it comes from. Is it ancient methane trapped in the subsurface and slowly leaking out? Is it produced by active geological chemistry occurring deep beneath the surface? Or could it be the signature of microbial life persisting in isolated pockets where liquid water still flows? The answer remains elusive. Methane molecules do not carry labels identifying their origin. To distinguish biological methane from geological methane requires detailed isotopic analysis, measurements that have not yet been conclusively obtained. The methane mystery exemplifies the challenge of astrobiology. Detecting life requires not just finding interesting chemistry, but proving that chemistry is biological in nature. Some scientists propose an even more radical possibility: panspermia, the hypothesis that life did not originate independently on Mars and Earth, but traveled between them. Billions of years ago, when Mars had a thick atmosphere and liquid water flowed across its surface, asteroid impacts would have ejected rocks into space. Some of those rocks, carrying dormant microbes, could have drifted through the solar system and eventually fallen to Earth. Conversely, Earth rocks could have seeded Mars. If this is true, then life on Mars and life on Earth may share a common ancestor. We may not be searching for alien life at all, but for distant relatives, biological cousins separated by time and space. The concept challenges the traditional narrative of life arising spontaneously on Earth. Instead, life may be a cosmic phenomenon, distributed across worlds by the violent mechanics of planetary collisions. Panspermia does not answer whether life exists on Mars today, but it reshapes the question: could Mars have been the origin point for all terrestrial life? The search for life on Mars is ultimately a search for biosignatures, subtle indicators that distinguish living systems from sterile chemistry. Biosignatures include specific patterns of isotopes that life preferentially uses, complex organic molecules that are difficult to produce abiotically, and atmospheric gases in disequilibrium, present in combinations that non-biological processes cannot sustain. But identifying a true biosignature is extraordinarily difficult. Chemistry on Mars is strange, influenced by perchlorate salts, intense ultraviolet radiation, and oxidizing conditions that destroy organic molecules near the surface. What appears to be a sign of life might be an artifact of these harsh conditions. What seems like sterile chemistry might mask biological activity occurring too slowly or too subtly for our instruments to detect. The search is further complicated by contamination concerns. Every spacecraft carries trace amounts of Earth microbes. Distinguishing between Martian biology and accidental contamination is a challenge that requires meticulous planning and extraordinary caution. The biological question on Mars is not one question, but many layered upon each other. Did life ever arise on ancient Mars when the planet was warm and wet? If it did, does it persist today in subsurface refuges? If it exists, is it related to Earth life, or is it a second genesis, an independent origin that would prove life is not a singular accident, but a universal inevitability? And if no life exists on Mars today, does the absence teach us something equally profound? That habitability alone is not enough. That life requires conditions so precise and improbable that Earth may be rare beyond comprehension. The answers will not come easily. They will emerge gradually, data point by data point, sample by sample, as rovers drill deeper, as instruments grow more sensitive, and as humanity eventually sends astronauts to sift through Martian soil with their own hands. The biological question is a journey without a guaranteed destination. But in asking it, We transform Mars from a cold, distant world into a place of profound significance. Whether life exists there or not, the search itself reveals who we are, a species that looks beyond itself, seeking connection, understanding, and perhaps, somewhere in the rust-colored dust of another world, a reflection of our own origins staring back. As we study Mars through decades of observation, certain features emerge that resist simple explanation. These are not mere curiosities catalogued and filed away. They are questions written in stone and ice, shadows cast across our understanding, landforms so extreme they challenge the very physics we thought governed planetary formation. To explore these anomalies is to venture beyond what we think we know about Mars, and into territory where competing theories clash, where data contradicts expectation, and where the planet itself seems to whisper secrets we are only beginning to hear. The first of these anomalies towers above all others, quite literally. Olympus Mons rises from the Martian surface like a monument to forces we struggle to comprehend. At 16 miles high, it is nearly 3 times the height of Mount Everest, stretching so far into the thin Martian atmosphere that its summit peers into the edge of space itself. Its base spans an area roughly the size of Arizona, and its cliffs drop in sheer escarpments up to 5 miles tall in places. If you stood at its center, the horizon would curve away in all directions, the mountain's edges lost beyond sight, invisible over the curvature of the planet itself. But Olympus Mons is not alone. It sits atop the Tharsis Bulge, a massive volcanic plateau that contains not one, but several enormous shield volcanoes, along with vast networks of canyons and fractures radiating outward like cracks in a frozen pond. The Tharsis region is so massive, so elevated, that it has measurably altered Mars's center of gravity. This is not simply a mountain range. It is a geological event of planetary proportions, one that has shaped the entire world around it. The question that haunts planetary scientists is simple yet profound. Why? Why is Olympus Mons so impossibly large compared to anything on Earth? Why did Mars produce volcanoes that dwarf our tallest peaks? The answer lies partly in Mars's relationship with time and geology. On Earth, tectonic plates constantly shift, carrying volcanic hotspots across the surface and distributing volcanic material over vast distances. Hawaii's chain of islands tells the story of a single hotspot beneath a moving plate, creating island after island as the Pacific plate drifts westward. But Mars has no plate tectonics. Its crust is stationary, frozen in place for billions of years. When a volcanic hotspot emerges on Mars, it stays in one location, building upward relentlessly, century after century, millennium after millennium, until gravity itself becomes the only limit to its growth. Yet even this explanation feels incomplete. Mars's lower gravity, roughly 1/3 that of Earth, allows structures to rise higher before collapsing under their own weight. But the sheer scale of Olympus Mons suggests volcanic activity sustained over unimaginable stretches of time. Some estimates suggest the mountain may have been active for hundreds of millions of years, possibly even sporadically erupting into relatively recent geological history. The youngest lava flows on its slopes may be only a few million years old, a mere moment in planetary time. What internal engine could power such prolonged volcanic fury on a planet we consider geologically dead? The Tharsis Bulge presents its own mysteries. This enormous raised region is not simply a volcanic plateau. It is a wound in the planet's crust, a place where Mars seems to have swollen from within. The mass of Tharsis is so great that scientists believe it may have caused Mars's rotational axis to shift, reorienting the entire planet. Imagine forces powerful enough to tip a world on its axis. What combination of heat, pressure, and time could create such a phenomenon? Some researchers propose that Tharsis formed early in Mars's history, when the planet's interior was still molten and active, perhaps during a period of massive mantle upwelling. Others suggest it represents the ghost of ancient tectonic activity, a final expression of geological forces before Mars's core cooled and fell silent. Moving beyond Tharsis, we encounter Mars's most dramatic geographical mystery, the hemispheric dichotomy. The northern and southern hemispheres of Mars are not merely different, they are opposites, as if two separate worlds were welded together at the seam. The southern highlands are ancient, heavily cratered, elevated terrain, scarred by billions of years of impacts. The northern lowlands are smooth, flat, and lie several miles lower in elevation, with far fewer craters. The boundary between them is not gradual. In places, it is a cliff face stretching thousands of miles, a continental divide of staggering proportions. No other planet in our solar system exhibits such a stark division between hemispheres. The Earth has continents and oceans, but they are scattered, distributed unevenly across the globe. Mars's dichotomy is absolute, cleanly splitting the planet into two halves. Competing theories attempt to explain this divide, but none are without complications. One hypothesis suggests that billions of years ago, during the solar system's violent youth, a massive object, perhaps the size of Earth's moon, struck Mars in the northern hemisphere. The impact would have blasted away crust and mantle, lowering the northern hemisphere by miles and creating the smooth plains we see today. Computer simulations show such an impact is plausible, but physical evidence remains elusive. Where is the massive impact basin? Why don't we see clear signs of such a catastrophic collision? Another theory proposes that the dichotomy formed through internal processes. Perhaps early in Mars's history, convection currents in the planet's mantle concentrated on one side, creating a region of thinner crust in the north while building up thick crust in the south. This would explain the elevation difference without requiring a cataclysmic impact. Yet it raises new questions. Why would such asymmetric convection occur? What forces would drive such lopsided geological activity? A third possibility blends both ideas. Perhaps an impact triggered the internal processes, or vice versa. Perhaps Mars's early geology was already becoming asymmetric when a massive collision amplified and locked in the division. The truth may be layered, complex, a story told in chapters we are only beginning to read. As we examine Mars's surface more closely, other anomalies emerge, smaller in scale but no less intriguing. Crater patterns across Mars reveal puzzles about the planet's history. Some craters appear impossibly fresh, their rims sharp and their interiors pristine, suggesting they formed recently in geological terms. Others show evidence of erosion by water or wind, their features softened by processes that may have occurred billions of years ago or perhaps more recently than we realize. Certain craters contain layered sediments, suggesting they once held lakes. But the timing and duration of these lakes remain uncertain. Did they exist for thousands of years or merely days after an impact melted underground ice? Then there are the recurring slope lineae, dark streaks that appear on Martian slopes, during warm seasons and fade during cold periods. When first discovered, they seem to offer tantalizing evidence of liquid water flowing on Mars's surface today. The streaks descend steep slopes, behaving like water stains, appearing in warmer months and vanishing in colder ones. Yet spectroscopic analysis revealed the presence of perchlorates, salts that lower water's freezing point, allowing briny flows at temperatures where pure water would freeze. But questions linger. Are these truly water flows, or are they dry, granular avalanches triggered by seasonal changes? Do they represent subsurface aquifers, bleeding slowly into sunlight, or merely dust and sand responding to thermal cycles? Different research teams propose different answers, and the lineae themselves seem to shift with each new observation, sometimes appearing exactly as predicted, sometimes defying explanation. Mars's seasonal changes add another layer of mystery. The planet experiences dramatic seasonal variations, with polar ice caps that grow and shrink, advancing and retreating with the Martian year. But the patterns don't fully match our atmospheric models. Dust storms, for instance, sometimes grow to planetary scale, shrouding the entire world in a haze that lasts for months. We can predict some of these storms, but others emerge without warning. The mechanisms that trigger global dust events remain partially understood, as if Mars's atmosphere follows rules we haven't fully deciphered. Why do some local storms explode across hemispheres while others remain contained? What invisible threshold determines the difference? Each anomaly, each unexplained feature, adds pieces to the larger Martian puzzle. Olympus Mons speaks of prolonged internal heat. The hemispheric dichotomy hints at ancient violence or asymmetric evolution. Crater patterns whisper of water, wind, and time. Recurring slope lineae suggest processes still active today, perhaps cycles of freezing and thawing we've never witnessed on Earth. Seasonal atmospheric behavior reminds us that Mars is not a static museum, but a living system, albeit one vastly different from our own world. These anomalies are not obstacles to understanding Mars. They are invitations. They challenge us to think beyond terrestrial analogies, to imagine planetary processes that have no counterpart in our experience. They remind us that Mars is not a smaller, colder version of Earth. It is its own world, shaped by forces and histories that are uniquely Martian. As our instruments improve and our observations multiply, we do not find answers so much as deeper questions, richer mysteries, a planet that reveals itself slowly, one anomaly at a time. In the quiet halls of museums and research laboratories across Earth, the rest fragments of Mars itself. Not photographs, not data, but actual pieces of the red planet, carried across millions of miles of space by forces beyond human design. These Martian meteorites, perhaps 50 or 60 confirmed specimens worldwide, are messengers from another world, and they tell a story far stranger than we might imagine. A story not of two separate planets, but of two worlds whose fates have been intertwined since the solar system's violent birth. Each Martian meteorite began its journey in a moment of cosmic catastrophe. An asteroid or comet struck Mars with such force that rock was ejected completely from the planet's gravitational embrace, flung into the void at speeds exceeding escape velocity. These fragments drifted through space for thousands, sometimes millions of years, following invisible orbits governed by the sun's gravity until, by chance or fate, their paths crossed Earth's. They fell as shooting stars, unnoticed except for the brief flash of friction as they descended through our atmosphere. When scientists first examined these rocks, they found something remarkable. Trapped within the crystalline structure were tiny pockets of gas, preserved like messages in bottles. The composition of these gases matched precisely the atmospheric measurements taken by Viking landers on Mars in the 1970s. This was not Earth rock. This was genuine Martian material, and it carried within it the chemical signature of another world. But what these meteorites revealed went far beyond simple identification. Some specimens, like the famous ALH 84001, discovered in Antarctica, contained structures that sparked one of the most profound debates in modern science. Microscopic formations within the rock resembled, at least superficially, fossilized bacteria. While the scientific community remains divided on whether these truly represent evidence of ancient Martian life, the possibility alone transformed our understanding of what Mars might have been. The existence of Martian meteorites on Earth raises a fascinating question. If material can travel from Mars to Earth, might it also travel in the opposite direction? The answer is an undeniable yes. Throughout the solar system's history, Earth and Mars have been exchanging material in a slow, cosmic conversation spanning billions of years. This exchange is called panspermia, and it operates on timescales that dwarf human civilization. When massive asteroids strike Earth with sufficient force, fragments of our planet are similarly ejected into space. Some of these fragments, governed by the intricate dance of orbital mechanics, eventually find their way to Mars. The process works in both directions, a planetary exchange program that has operated since the earliest days of the solar system. What makes this exchange particularly intriguing is timing. During the period known as the Late Heavy Bombardment, roughly 4 billion years ago, both planets were subjected to an intense barrage of asteroid impacts. This was an era of cosmic violence, when worlds were still forming and space was filled with debris from the solar system's chaotic youth. During this period, the exchange of material between Earth and Mars would have been at its peak. Millions of rocks, some perhaps the size of buildings, were launched from each planet's surface and sent wandering through space. Here we encounter one of the most radical ideas in planetary science. What if life on Earth did not originate here at all? What if instead the first living organisms arose on Mars and were transported to Earth aboard meteorites during this ancient bombardment? This concept, sometimes called the Mars First hypothesis, is not mere speculation. It is grounded in a curious fact about early planetary conditions. Mars, being smaller than Earth, cooled more quickly after its formation, while Earth's surface remained a molten hellscape, bombarded by asteroids and comets. Mars may have developed stable conditions suitable for life much earlier. Ancient Mars possessed liquid water, a protective atmosphere, and volcanic activity that could have provided chemical energy. It may have been, for a brief window of time, more habitable than Earth itself. If microbial life arose on Mars during this early epoch, it could have survived the journey to Earth. Studies have shown that certain bacteria can endure the vacuum of space, extreme radiation, and the violent shock of meteorite impacts. Protected within rocks, these organisms might remain viable for millions of years, entering a state of dormancy until conditions improve. When these Martian rocks fell to early Earth, any hitchhiking microbes would have found a world gradually becoming hospitable. They would have awakened in warm pools, volcanic springs, perhaps even shallow seas. From there, life would spread, diversify, and eventually evolve into every living thing we see today, from bacteria to redwood trees to human beings. If this hypothesis is correct, we are all, in a very real sense, Martians. Our ancestors simply took the long way home. The evidence neither confirms nor refutes this idea. It remains one of those beautiful uncertainties that science occasionally encounters, a possibility that reshapes our understanding regardless of whether it proves true. What it does reveal is that Earth and Mars are not isolated worlds. They are siblings, connected by invisible threads of material exchange. Their histories written not in separate chapters, but in overlapping narratives. Yet beyond this exchange of rock and perhaps life, Mars and Earth share another, more sobering connection. They serve as mirrors of divergent evolution. Two planets that began similarly but ended as opposites. Mars is, in many ways, Earth's cautionary tale. Both planets formed in the same stellar nursery, condensing from the same primordial disk of gas and dust. Both possessed atmospheres, liquid water, and geological activity. For their first few 100 million years, Mars and Earth may have looked remarkably similar. But then their paths diverged dramatically. Mars lost its magnetic field early in its history, perhaps within the first billion years of its existence. Without this protective shield, the solar wind, a relentless stream of charged particles from the sun, began stripping away the Martian atmosphere. Layer by layer, molecule by molecule, the atmosphere was peeled into space. As the atmosphere thinned, temperatures dropped, liquid water froze or evaporated, rivers dried, lakes vanished. The planet that might have cradled life became a frozen desert. Earth, by contrast, maintained its magnetic field, generated by the churning motion of molten iron in its outer core. This invisible shield deflected the solar wind, preserving our atmosphere and allowing water to remain liquid on the surface. The difference between a living world and a dead one came down to planetary size and internal heat. Mars, smaller and cooling faster, could not sustain the geological processes necessary to maintain its protective field. Studying Mars forces us to confront uncomfortable truths about planetary fragility. Atmospheres are not permanent. They can be lost, not through sudden catastrophe, but through slow erosion over geological time. Mars demonstrates what happens when a planet loses its ability to hold onto its air. It becomes a world where water cannot exist in liquid form, where temperatures swing wildly between day and night, where the surface is bombarded by radiation from space. This lesson resonates profoundly in our current era. Earth's atmosphere is changing, not because of natural geological processes, but because of human activity. While the timescales are vastly different, Mars reminds us that atmospheres are dynamic systems, vulnerable to disruption. The red planet shows us that a world with rivers and rain can become a world of dust and ice if the conditions that maintain habitability are allowed to fail. Mars teaches us about thresholds and tipping points. There was a moment in Martian history, perhaps lasting millions of years, when the planet teetered on the edge. Atmospheric pressure was falling, but liquid water still flowed occasionally. Greenhouse gases were declining, but warmth lingered in protected valleys. Then, gradually, irreversibly, Mars crossed a threshold from which it could not return. The atmosphere became too thin to support liquid water. Temperatures dropped permanently, below freezing. The planet entered a state from which, without external intervention, it cannot escape. Understanding this transition is not merely an academic exercise. It illuminates the factors that keep Earth habitable and the forces that could potentially undermine that habitability. Mars is a laboratory, a natural experiment in planetary death, and its lessons are preserved in every dry riverbed, every ancient lakeshore, every mineral formation that speaks of water long vanished. The cosmic factors that led to such different fates were subtle but decisive. A slightly larger size might have allowed Mars to retain internal heat longer, maintaining its magnetic field and protecting its atmosphere. A different orbital position, closer to the Sun's warmth, might have compensated for the loss of atmospheric pressure. These variables, determined by the random chaos of planetary formation, sealed the destiny of two worlds billions of years ago. In the end, the story of Mars and Earth is not one of separation, but of connection. We are bound together by exchanged material, by shared origins, by parallel histories that diverged at a critical juncture. Every Martian meteorite that falls to Earth reminds us that planetary boundaries are permeable, that worlds influence one another across vast distances and timescales. Mars is not merely a neighbouring planet. It is a teacher, a warning, and perhaps even an ancestor. Its silent deserts hold secrets about Earth's past and potentially its future. As we study Mars, we are not looking outward at something alien. We are looking sideways at what we might have been, or what we might yet become. We stand at a threshold unlike any in the history of planetary exploration. The Mars we study today is not the Mars of decades past, not because the planet has changed, but because we have. Our eyes have sharpened. Our instruments have awakened. Technology has transformed us from distant observers into intimate investigators of a world that once existed only as a red dot in the night sky. Every generation of Mars missions has peeled back another layer of mystery, revealing not just answers, but deeper, more profound questions. The revolution is not simply in what we discover, but in how we discover it. Each technological leap reshapes our understanding so fundamentally that Mars becomes, in essence, a new world with each arrival. Consider Perseverance, NASA's most advanced rover, which touched down in Jezero crater in February 2021. This is not merely a vehicle. It is a mobile laboratory carrying instruments so sophisticated they can analyze the chemical composition of rocks with precision that would have seemed impossible just 20 years ago. Its robotic arm extends with delicate precision, grinding into ancient stones, examining minerals that last felt water billions of years ago. The rover's cameras capture Mars in such extraordinary detail that geologists on Earth can study rock formations as if standing beside them, examining textures, layers, and patterns that tell stories of ancient rivers, vanished lakes, and atmospheric transformations. But perhaps the most revolutionary aspect of Perseverance is not what it carries, but what it brought with it. Tucked beneath its belly during landing was Ingenuity, a helicopter drone weighing just 4 pounds. When Ingenuity lifted off the Martian surface for the first time, it achieved something that had never been done: powered, controlled flight in the thin atmosphere of another world. Mars's atmosphere is less than 1% the density of Earth's. Flying there is akin to flying at 100,000 feet altitude on our planet, far higher than any helicopter has ever flown here. Ingenuity was designed as a technology demonstration, meant to fly perhaps 5 times over 30 days. Instead, it has flown dozens of missions, scouting terrain ahead of Perseverance, reaching areas the rover cannot access, revealing landscapes from perspectives never before available. This small drone has transformed Mars exploration from a ground-level journey into a three-dimensional investigation. We no longer crawl across Mars. We soar above it. The true revolution, however, extends far beneath the surface. Ground-penetrating radar has become one of our most powerful tools for seeing what lies hidden below the rusty dust. Instruments like RIMFAX, mounted on Perseverance, send radar pulses deep into the ground, listening for echoes that reveal buried layers, ancient water tables, and geological structures invisible from above. These subsurface maps are rewriting Martian history in real time. What appears as flat, featureless terrain from the surface may hide river deltas, lava tubes, or ice deposits meters below. We are learning that Mars is not just a surface to traverse, but a volume to explore, a planet with hidden dimensions that extend downward into mysteries we are only beginning to perceive. Meanwhile, orbiting spacecraft equipped with advanced radar systems peer through dust storms and darkness, mapping subsurface ice across vast regions of the planet. The Mars Reconnaissance Orbiter's Sharid instrument has revealed layers of ice and rock extending hundreds of feet below the surface near the poles. These discoveries suggest that Mars holds more frozen water than previously imagined, locked away in geological archives that preserve not just ice, but a record of climate cycles spanning millions of years. Sample collection represents another frontier in our technological evolution. Perseverance is not just studying Mars, it is gathering pieces of it. The rover carefully selects rocks that display particular characteristics: ancient lake sediments, volcanic materials, rocks bearing signs of water alteration. Using a sophisticated coring drill, it extracts samples the size of a piece of chalk, seals them in ultra-clean tubes, and stores them in its belly. These samples, currently cached on the Martian and surface, await a future mission that will collect them and launch them into orbit, where another spacecraft will capture them and begin the long journey back to Earth. This planned Mars sample return mission is perhaps the most ambitious robotic endeavour ever conceived. It requires multiple spacecraft working in coordination across 2 planets, a landing system, a fetch rover, a rocket that will launch from Mars for the first time in history, and an orbiter capable of rendezvous in Martian orbit before returning to Earth. The timeline stretches into the 2030s, yet the significance cannot be overstated. When those samples arrive on Earth, they will be studied with instruments far too large and complex to send to Mars. Scientists will analyze them with precision measured in parts per trillion, searching for organic molecules, examining isotopic ratios, looking for biosignatures that could reveal whether life ever emerged on our neighboring world. But even as we plan these mechanical marvels, another revolution unfolds quietly in the background. Artificial intelligence and machine learning are transforming how we understand Mars in ways both subtle and profound. The volume of data streaming back from Mars is staggering. A single day of rover operations can generate thousands of images, spectroscopic readings, atmospheric measurements, and geological surveys. No human team could analyze it all in real time. This is where AI steps forward. Machine learning algorithms now scan images autonomously, identifying rocks of interest, detecting unusual features, highlighting potential discoveries that might otherwise be lost in the flood of data. Perseverance can analyze a rock and decide independently whether it warrants closer study, all without waiting for instructions from Earth. This autonomy accelerates exploration exponentially. The rover makes decisions in minutes that would otherwise take days when accounting for the communication delay between planets. AI also helps us see patterns invisible to human eyes. By analyzing thousands of images, machine learning systems can identify subtle changes in terrain, track dust devil movements, monitor cloud formations, and even predict weather patterns. These systems learn from every observation, becoming more sophisticated with each passing sol, the Martian day, refining our understanding through computational power that complements human intuition. Looking ahead, upcoming missions promise to deepen this technological revolution further. The European Space Agency's Rosalind Franklin rover, scheduled to launch in the coming years, will carry a drill capable of reaching 2 meters below the surface, deeper than any previous Mars mission. At those depths, organic molecules might be preserved from the harsh radiation that sterilizes the surface. The rover will search not just for signs of ancient life, but for complex chemistry that might reveal Mars's potential for biology. NASA's proposed Mars Ice Mapper mission aims to create detailed three-dimensional maps of subsurface ice deposits, identifying locations where future human missions might access water resources. Other concepts in development include seismic networks to study Marsquakes, balloons that would drift through the atmosphere for months, and eventually, sample return missions that could retrieve material from specific locations, identified as high priority for astrobiology. Each advance reveals not just answers, but the limitations of our previous understanding. When Mariner 4 flew past Mars in 1965, it captured 22 images showing a cratered, moon-like surface. Scientists concluded Mars was dead, geologically inert, devoid of interest beyond historical curiosity. Yet that conclusion reflected not the nature of Mars, but the limitations of our technology. Better cameras revealed volcanoes. Better instruments detected water. Better analysis suggested the possibility of life. This pattern persists with every mission. The technology revolution is not a march toward final understanding, but a journey into ever-deepening complexity. Ground-penetrating radar shows us what lies beneath, and beneath that, we imagine deeper layers still unexplored. AI helps us process vast data streams, yet we recognize that patterns exist beyond even algorithmic detection. Sample return will answer fundamental questions about Mars's past, but it will surely raise questions about its future we cannot yet formulate. The tools we create to explore Mars change not just what we see, but who we are as explorers. We are no longer limited by distance or danger. Our machines extend our senses across space, allowing us to touch rocks we will never reach, to breathe atmospheres that would kill us, to stand on surfaces where no human may walk for generations. Yet through these instruments, we are there, present in every measurement, every image, every discovery. As we continue to develop new technologies, we must remember that each tool is both a window and a mirror. It shows us Mars, but it also reflects our capacity for curiosity, our drive to understand, our willingness to invest years and resources into answering questions that have no immediate practical application. The technology revolution on Mars is ultimately a human revolution, a transformation of how we relate to the cosmos and our place within it. Mars awaits our next generation of instruments with patient indifference. The planet does not change because we study it, yet we change profoundly with every new tool we create, every new question we ask, every new mystery we uncover. The revolution continues, not because Mars is unknowable, but because knowing Mars transforms us in ways we cannot predict until the knowledge arrives. We stand now at a threshold of understanding, gazing back at Mars not as a dead world frozen in time, but as a planet still writing its story. The discoveries of recent years have not merely added details to our knowledge, they have rewritten the narrative entirely. Mars is no longer the cold, lifeless monument to planetary death that we once imagined. It is a world in transition, a place where water still flows beneath the surface, where methane rises mysteriously from hidden sources, where ancient riverbeds whisper of oceans that may yet return in some distant epoch. The Mars we think we know is dissolving before our eyes, replaced by something far stranger and more compelling. For decades, we approached Mars with a single question: is there life? But perhaps we have been asking the wrong question all along. The evidence accumulating from rovers, orbiters, and spectrometers suggests we should instead ask, when was Mars alive? And could it be alive still? Every measurement of subsurface ice, every detection of organic molecules, every observation of seasonal changes reshapes our understanding. Mars is not a museum piece preserved in amber. It is a living laboratory of planetary evolution, caught between what it was and what it might yet become. The philosophical shift this requires is profound. We have grown accustomed to thinking of planets as having life cycles with clear beginnings and endings. A planet forms, evolves, perhaps supports life, then dies, its atmosphere stripped away, its core frozen, its surface silent forever. Mars appeared to fit this narrative perfectly, a cautionary tale of planetary decline, a world that lost its magnetic field, then its atmosphere, then its water, descending inexorably into the frozen wasteland we observe today. But the hidden science reveals something more nuanced and extraordinary. Mars did not simply die, it transformed. Beneath that rust-colored surface lies an entire world we are only beginning to glimpse. Liquid water persists in vast underground reservoirs, protected from the harsh surface conditions by kilometers of rock and ice. Some of these aquifers may be warmed by residual geothermal heat, creating environments where temperatures remain above freezing year-round. In these hidden spaces, conditions may not be so different from the deep earth environments, where extremophile bacteria thrive in total darkness, drawing energy not from sunlight, but from chemical reactions between water and rock. If life emerged on ancient Mars when its surface resembled early Earth, could descendants of those organisms still persist in these subterranean refuges? The discovery of seasonal methane variations adds another layer to this mystery. On Earth, over 90% of atmospheric methane is produced by biological processes. The methane detected on Mars appears and disappears with the seasons, suggesting an active source that responds to environmental changes. While geological processes can also produce methane, the seasonal variation is difficult to explain through geology alone. Some researchers propose that microorganisms dwelling beneath the surface may become more active during Martian summer, releasing methane that seeps upward through cracks in the rock. Others suggest that ancient methane trapped in subsurface ice is released as seasonal temperature changes cause the ice to expand and contract. Both explanations point to the same conclusion. Mars is geologically and perhaps biologically active in ways we never anticipated. This realization transforms how we must approach future human exploration. For decades, Mars has been viewed as a destination for pioneers willing to inhabit a hostile, barren world. The challenge was framed as one of survival, how to extract oxygen from the thin atmosphere, how to grow food in sterile soil, how to shield habitats from lethal radiation. These challenges remain, but the emerging picture of Mars suggests possibilities we had not seriously considered. If vast reservoirs of liquid water exist underground, future settlers would not need to extract moisture from the atmosphere or melt surface ice. They could tap directly into aquifers that may contain billions of litres of water, perhaps already filtered and purified by its journey through Martian rock. The presence of subsurface water also raises the possibility of geothermal energy. While Mars's core has cooled considerably since its youth, localized heat sources may still exist in volcanic regions or areas where radioactive decay warms the surrounding rock. Future Martian colonies might be established not on the surface, but underground, in caverns warmed by planetary heat and protected from radiation by natural shielding. Instead of constructing pressurized domes on a frozen desert, humanity might create subterranean cities in environments far more hospitable than the surface suggests. Mars may offer not just survival, but genuine habitability if we look beneath the obvious. Yet this new understanding brings profound responsibilities. If Mars harbors life, even microbial life clinging to existence in subsurface waters, then human exploration becomes infinitely more delicate. We would be visitors to a biosphere not our own, with obligations to preserve and protect whatever native ecosystems we discover. The hidden science that changes everything about Mars also changes everything about how we must explore it. Each drilling operation, each sample collection, each human footstep must be carefully considered to avoid contaminating or destroying what may be the only other place in the universe where life took hold. The broader implications extend far beyond Mars itself. For centuries, we have wondered whether Earth is unique, whether the emergence of life requires such precise conditions that it occurs only once in a galaxy, or perhaps only once in an observable universe. Mars provides a test case extraordinarily close to home. If we discover that life emerged independently on Mars during its ancient wet period, it would suggest that life is not a miraculous accident, but an almost inevitable consequence when water, energy, and organic chemistry converge. The universe would suddenly seem far less lonely. Even if we find that Mars is, and always has been, sterile, the discovery would be equally profound. Two planets, formed from the same disk of material, orbiting the same star, both possessing liquid water for billions of years, yet only one developing life. Such an outcome would suggest that the transition from chemistry to biology is far more difficult than we imagine, requiring factors we have not yet identified. Either answer transforms our understanding of our place in the cosmos. Mars also serves as a mirror reflecting Earth's possible futures. The planet once had a thick atmosphere, flowing rivers, perhaps even oceans. Climate models suggest it may have been warmer than Earth is today. Then something changed. Its magnetic field collapsed. Solar winds stripped away its atmosphere. Surface water evaporated or froze, and the planet entered the cold state we observe now. This is not merely ancient history. It is a warning and a lesson about planetary fragility. The forces that transformed Mars operate throughout the universe, and understanding them helps us appreciate how delicate the balance is that maintains Earth's habitability. The hidden science of Mars reveals something deeper than geological facts and chemical measurements. It reveals that planets are not static objects. but living systems in the most profound sense, not necessarily biological, but dynamic, evolving, responding to internal and external forces across timescales that dwarf human civilization. Mars has been many worlds across its 4.6 billion year history. A warm, wet planet with rivers and lakes. A volcanic world with eruptions that dwarfed anything Earth has experienced. A frozen desert where water retreated underground. And perhaps now transitioning towards something new as the sun gradually brightens and solar output increases over the coming billion years. To reimagine Mars is to accept that we are not observing a corpse, but catching a momentary glimpse of a world between chapters. What we see today is not Mars's final form, but simply its current state. In another billion years, if conditions change, if volcanic activity resurges, if the planet's interior warms through some process we do not yet understand, liquid water might return to the surface. The cycle could begin again. Or Mars might remain frozen, a monument to possibilities unrealized, until the sun expands into a red giant and consumes it entirely. The bigger picture is not just about Mars. It is about how we understand the nature of worlds themselves. Every planet is a story still being written. Every moon a chapter in a longer tale. The hidden science that changes everything about Mars changes everything about how we view planetary evolution throughout the universe. We are no longer simply cataloguing dead worlds and living ones. We are learning to read the narratives written in rock and ice, to see not just what is, but what was and what might yet be. As we continue to explore Mars with ever more sophisticated instruments, as rovers drill deeper and orbiters peer farther into the subsurface, we are not merely gathering data. We are learning a new language, one spoken in seasonal methane variations and ancient riverbeds, in subsurface lakes and volcanic minerals. Mars is teaching us to see beyond the surface, to recognize that the most profound truths about worlds may lie hidden from easy observation, waiting for those patient and curious enough to look deeper. The Mars we think we know is gone, replaced by something infinitely more interesting, a world still full of secrets, still evolving, still capable of surprising us. And in that realization lies perhaps the greatest discovery of all. The universe is not a collection of finished objects, but an ongoing process, and we are privileged to witness one small chapter in one small corner of an infinite cosmic story that continues to unfold around us, inviting us always to look again, to question further, to imagine beyond what we think we know. We have journeyed to Mars, not as we thought it was, but as it truly is. A world that defies our expectations at every turn, challenging us to see beyond the rust-colored surface and into the depths of mysteries that reshape our understanding of planetary evolution itself. Mars is not the dead world of popular imagination. Beneath its frozen deserts lie ancient lakebeds that once held more water than the Arctic Ocean. Within its polar caps rest layers of ice and dust that chronicle climate changes spanning millions of years. Below its crust, liquid water may still flow through networks of aquifers, hidden from the sun but not from possibility. The Mars we think we know is merely a fragment of the Mars that exists, a single chapter in a story written across 4 billion years. We have learned that Mars once possessed a magnetic field, a protective shield that vanished in ways we are only beginning to comprehend. We have discovered that its atmosphere was stolen, stripped away by solar winds that now carve directly into the planet's upper layers. We have found organic molecules in ancient rocks, methane plumes that appear and vanish with the seasons, and geological features that hint at volcanic activity, far more recent than any textbook would have predicted just decades ago. Yet, for every answer Mars provides, it presents 10 new questions. Why did its magnetic field collapse? Where did all the water go? If life ever emerged in those ancient oceans, what traces might remain in the deep subsurface? And perhaps most intriguingly, what role does Mars play in understanding not just planetary science, but the very conditions that make life possible anywhere in the universe? Mars has become our laboratory for understanding transformation. It shows us what Earth might have become under different circumstances, what Venus avoided by chance, what countless exoplanets across the galaxy may be experiencing at this very moment. In studying Mars, we are not merely exploring another world. We are decoding the fundamental rules that govern planetary destiny. The technology revolution has changed everything. Rovers traverse its surface with artificial intelligence, making decisions millions of miles from human oversight. Orbiters map its subsurface with ground-penetrating radar, revealing structures invisible to previous generations. Spectrometers analyze Martian rocks with precision that would astound the scientists who first dreamed of visiting the red planet. And soon, sample return missions will bring pieces of Mars to Earth, allowing us to study another world with the full power of terrestrial laboratories. But the greatest revolution is not technological, it is perceptual. Mars is no longer a distant curiosity or a cold, forbidding wasteland. It is a world in transition, perhaps even a world on the threshold of hosting human presence. The hidden science we have explored tonight, the underground water, the recurring slope lineae, the methane anomalies, the preserved organic chemistry, these are not merely academic discoveries. They are signposts pointing toward a future where Mars becomes part of humanity's story, not just as observers, but as participants. The new Mars that awaits us is one of endless possibility. It is a world where robots, and eventually humans, will drill into ancient ice, searching for preserved biosignatures. A world where sealed lava tubes may offer natural habitats for future explorers. A world where the thin whisper of atmosphere might one day thicken again through human ingenuity, transforming the planet over centuries into something neither fully natural nor entirely artificial. Mars reminds us that the universe does not reveal its secrets quickly or easily. It demands patience, curiosity, and the willingness to be surprised. Every new mission arrives with instruments more sensitive than the last. Yet Mars continues to astonish us, challenging our assumptions and forcing us to think more deeply about what it means for a planet to be alive, dormant, or somewhere mysteriously in between. As we close this journey through Mars's hidden science, we are left not with certainty, but with wonder. And that, perhaps, is exactly as it should be. The red planet has not finished teaching us. The story is still being written. If this exploration has changed how you see Mars, or sparked questions you had never considered, I invite you to like this video and subscribe to the channel for more journeys through the cosmos. Leave a comment below telling us where in the world you're listening from and what aspect of Mars fascinates you most. Your engagement helps these explorations reach others who share our curiosity about the universe. For those who wish to support the channel further, YouTube membership is available, though it is completely optional. This content will always remain free for everyone who seeks it. A new Mars awaits. Not the Mars of old assumptions, but one of ongoing revelation. And we, observers of this magnificent transformation, are privileged to witness its secrets slowly unfold, one discovery at a time. Until our next journey among the stars, keep looking up, keep questioning, keep wondering.